we are told the weight or the mass of the disk is 45 kilograms. And the coefficient of friction at A between the disk and the ground is 0.2. So we want the minimum value of m it would take to start motion, or the maximum value of m before there was motion. So m min for motion. AB is pinned at C, pinned at B to the disk. I assume C was right and up. I assume B was right and up in this picture. And then we're applying a moment of M on it. And picture number 2, the disk, they don't tell us the weight of this rod. They tell us the weight of the disk, equal and opposite forces at B from that pin connection. The normal force at A, it's contacting the ground at one point. And we expect that the disk would be sliding to the right, so FA, to counteract that impending motion. Picture 1 and picture 2 are both rigid bodies, so we can write 3 equilibrium equations from each of them. The 6 equilibrium equations we get are here. We have 7 unknowns. Unfortunately, all of the equations have at least 2 unknowns, and no 2 have the same 2 unknowns. So numerically, this is not as straightforward as a lot of the other ones we've seen before. But the equations, though, are at least written. We need to make this a solvable system, so we need at least one more equation. What's the at least one more equation we can add to make this solvable? We are looking for what's happening on the verge of slipping. We know, so that means that the friction force at A is at its maximum value. We're on the verge of slipping. We know mu A is 0.2, and the normal force we don't know as a number yet, but we know it's NA. The 7th equation, we now have 7 equations and 7 unknowns. This doesn't help us, or we can't just pop this in and easily solve it still, but we have, at least we know it's a solvable system. I didn't try solving it by hand, but I just did this one numerically. If we solve it numerically, from these 7 equations, 7 unknowns, we find the m that causes it to be on the verge of slipping is 77.2 Newton meters.